All right, so our first little video dealt with units. That was our, stay dimensional homogeneous. That's our first tip. The second tip was when we do unit conversions uh, to multiply by some form of unity. Our third tip has to do with significant figures. And I'm sure you've dealt with significant figures here, but we really want to focus here on what they mean, on why do your teachers keep telling you to pay attention to significant figures? And significant figures really is a question of error um, and uncertainty. So when we take measured value, let's say I'm trying to measure, I don't know, how high I'm throwing a baseball, right? Or how high I can throw a baseball. We're going to get different values along the way. Okay, if this is height on our left. Um, and I'm going to come up with an average here, right? And I'm going to say this average is the height that I can, in general, I can throw a baseball this high. Occasionally go a little higher. Sometimes it won't go as high, but I want an average value. And so we have scatter here. And that's called random error. Okay. Um, Systematic error arises because there's something wrong with um, the problem. Let's say that the way I was measuring it had some kind of error. My measuring stick was not very good, right? Or I forgot that I was wearing platform shoes that were giving me an extra 3 inches every time I threw the ball. Or my elbow was, hurting that day, and so it wasn't really as high as I could throw the ball. All of those would be systematic error. They would mean that every value in here was off by some given value. So random error is always going to happen. Systematic error is something we're trying to get rid of. And we do try to reduce random error as much as we can. But you're never going to get rid of that random error. Systematic error or bias is something that we want to try and deal with as best we can. Um, so how do we express the uncertainty of a value? Oftentimes we'll do it in a form like this, which is a plus minus form. And what this means is that the density of our fluid here lies somewhere between 41 kilograms per meter cubed less than 3,000 and 41 more than 3,000. So somewhere in that range. And we oftentimes will express that statistically as a percentage. We might say there's a 90% chance it lies between these two values. We can also write this value here as a percentage, because if I just say my uncertainty is 41 kilograms per meter cubed, it's hard to know if that's a large or a small value. But if we write it as a percentage, we know its relative size. So the error here is little e. The average value is a. And we can multiply this fraction out by 100 to get our uncertainty. And so 1.4% uncertainty is a relatively low uncertainty. So we might think, oh, okay, that value is pretty good, depending on what you're using it for. So uncertainty is always there. We can reduce it by taking more measurements, right? If I throw that baseball in the air, 1,000 times, I'll have a better average than if I just throw it 3 times. We can use a more accurate instrument. So instead of using a meter stick, we might use a laser or something to find out that height. And then to try to control our extraneous variables. These are the things that create systematic error, right? That make our answers wrong in a lot of ways. So I might take off my platform shoes, so I wasn't getting the extra height from those, or change whatever it is that is creating some kind of, I wait until my elbow heals so that I can get a better true value. So what does all this have to do with significant figures? Well, significant figures are an implicit expression of uncertainty. Okay, so when we write this, my mass is 12.7 kilograms, what we're really writing is my mass is somewhere between 12.65 kilograms and 12.75 kilograms. Okay, we're saying I know it to this degree of certainty. If I wrote instead 12 kilograms, I'd be saying, well, it's between 11.5 and 12.5. Okay, so that would be a less accurate number or a less certain number. This is one of the reasons we use scientific notation a lot, right? Because this value here tells me my uncertainty, right? This is different than 2.00 times 10 to the third. But this number doesn't tell me that, okay? I don't know if my significant figures here are 1, 2, 3, or 4. And so this doesn't give me that implicit expression of my uncertainty. We have some rules for dealing with this, and we'll talk about these. You can sort of look these over here. But essentially, when we multiply, we take the smallest number of SigFigs. And so here we have 3 SigFigs and 3 SigFigs. So our answer should have 3, even though when we put it in the calculator, it has a lot more. Okay? And that has to do with that implicit expression of accuracy, right? We've stated here how accurate these numbers are. And so we don't want an answer that's much more accurate than these, right? This one's saying I know it within this margin, which is 10 times more accurate than I knew the initial numbers. And so that's unlikely. So we set up these rules. And you can kind of look through that on your own. Same for addition, although the rule is different. In addition, we don't want to be any more accurate than our least accurate number, right? So here we have a number 11 kilometers that's only accurate to the ones digit. Well, our answer shouldn't be any more accurate than the ones digit, okay? Because this is saying somewhere between 10.5 and 11.5. So there's no way I can have an answer that says 19.1. Because there was a range of a full kilometer here in which I was saying I don't know that it fits in there. Okay, so it wouldn't make any sense to say that my answer is 18.8 because the range of error in this number is much larger than the range of error in that number. The big idea here is just remember these are guidelines, right? They're not strict rules. Some disciplines have strict rules that you always have to follow, but really what you're trying to do is just make sure you're not stating your answer with more certainty than you have reason to believe you have. Okay, so it's a way of being generous to your reader and saying, I only know this much.